everybody, welcome. We're going to spend about 60 minutes today just looking into the NFResNet paper. And can I please ask maybe if you want to raise your hands, just a quick show of hands just in the participants. If you know about the NFResNet paper, or if you've heard of it, or if you've seen it, I think there's an option to raise hands uh, in Zoom, or just put it in chat, just like say yes or no. I'm just very curious, just a quick. So we've got a bunch, we've got a mixed bunch. So some of us know about it, some of us don't know about it. In this 60 minutes today, we're going to be discussing the paper, and then we're going to be going into the question answers as well. Towards the end, it's not a question answer; it's more of a discussion. Towards the end of 15 minutes, and something that we do in our paper reading groups is towards the end we go. If you go to that link, let me copy paste it in the chat as well. It brings up a report. So it will bring up the paper reading group report, and this is June 8th, that's today, and we'll be looking at the characterizing signal propagation. So something that we do from most of our past paper reading groups is that based on this, because we have to stream it online as well, so it's just a lot of different places that people are attending this from. So it's just easier if we all put our comments in one place, and that's towards the end. But if you want to, start asking your questions, or you want to make comments, there'll be ample opportunity for us to talk to ourselves. There'll be ample opportunity to, for me to ask questions if there's some part of the paper that you don't understand. But we're going to be diving deep into this paper. Okay, so that's that. So that's the paper reading group. So with that being said, let's get into the NFResNet paper. And before we do get into the NFResNet paper, we want to start with ResNet. So the ResNet architecture. So usually I come with PowerPoint slides, but today I thought, let's just go through the paper. Let's go through the paper one by one, and we can have a look at what exactly is going on in the NFResNet paper. But we know that the ResNet paper looks something like this. So if I'm having a look at the 34 layer residual, I know that we start. So the first thing, the first thing that's there is the 7x7 conf, and this looks like it's called a stem, right? So that's the first thing. So we've got a stem here. And then this is the first block. The one in green is the second block. We keep going down. This is the third block, and this is the fourth block. So if you count the number of, basically it's a conv batch norm ReLU. So if you count, there's like 3 of these. So that's, this whole thing is counted as 1. So there's 3 of these. Conf batch num ReLU. There's 4 in here, there's 6 in here, and there's 3 in here. So that's the ResNet 34 sort of architecture. For every other architecture, the only thing that's different is that these numbers of layers will change. So for deeper architectures, if we go for ResNet, say, sorry, could I please ask it to mute? Sorry, could I please ask you to mute yourselves in case you've joined the call? Okay, so we've got a 3463 for a ResNet 50. And for a ResNet, say if you want to go deeper, then ResNet 100 looks different, and that's how there's these number of layers. So we just look at the 34, which is 3, 4, 6, 3. A 152 would have 3, 8, 36, 3. That's the ResNet architecture, but we want to understand exactly that. The one thing I do want to point out in the ResNet architecture is when we go from one block to another. So basically just this point here. So one block to another. So at the point where the first block finishes and the second block starts, you can see that we're going from 64 channels to 128 channels. And something else that happens is when the number of channels doubles, what happens is the image size is halved. So the height is halved and the width is halved as well. So we lose the spatial dimension. So So this is called a skip connection, the one on the right. It's called a skip connection. So this branch here is called the residual branch, and all of these are called skip connections. And then the point where there's a change in block, this skip connection is actually a convolution. So that's the basic idea of ResNet. With that being said, we are now ready to look into the NF-ResNet paper, which is this one. I'm characterizing signal propagation to close the performance gap in unnormalized networks. But as part of this, I think before coming to this, you would have also seen this, received this blog. So I ended up writing a blog about characterizing signal propagation to close the gap as well. And basically, what this blog is, it has everything you need to know about this paper, and it has also a code implementation in PyTorch. And we also plot the signal propagation plots that we see using PyTorch hooks. So after this, I do believe that today, once we have a good solid understanding of the NF-ResNet paper, then after this, it would be a good idea to go through this blog and just make sure that you understand everything that you did end up learning today. Cool. With that being said, let's kick in and let's start with characterizing signal propagation to close the performance gap in unnormalized ResNets. So this is the main part, unnormalized ResNets. And the idea is, in a ResNet, basically, when I said in the residual branch, so in a ResNet, the branch looks like this. You have a convolution, batch norm, ReLU. So that's one, and then convolution, batch norm, ReLU. I've just called it like this. So this is your input, and then that becomes your skip connection. But you can see how there's a batch norm in the ResNet everywhere. The idea is that we want to remove this batch norm. So we want to get away from it. That's the main idea. So we want to design ResNets without this batch norm. So let's have a look at the abstract. Batch norm is a key component in almost all state-of-the-art image classification classifiers, but it also introduces practical challenges. So batch norm has many advantages. It has many advantages, but it also comes with some disadvantages. It breaks, for example, these are one of the practical challenges. It breaks the independence between training examples within a batch, can incur compute and memory overhead, and often results in unexpected bugs. Building on recent theoretical analysis of ResNets and initialization, we propose, so this is the main bit, we propose a simple set of tools to characterize signal propagation on the forward pass. What that basically means, what the authors are trying to say here is that they're saying that they proposed a new way of having a look at how signal propagates from right at the beginning towards the end and throughout the whole architecture, basically. And they also say, crucial to our success is an adapted version of the recently proposed weight standardization. So I'll get into what weight standardization is once we get to that point. But basically, the batch norm, for those of you that know, the batch norm normalizes the activations, and weight standardization normalizes the convolution weights. But we'll get into this. Cool. So that's that. We are good for, so that's just the abstract. So the abstract is just the main idea usually in a paper, and the main idea is this: we want to replace the batch norm in ResNets, and we want to replace it. We want to design ResNets in a way that there's no normalization. And one thing I do want to point out, the reason why this is important is it's one of the very first papers. The NF-ResNet was the very first. Like, they had papers before the authors from DeepMind. They had papers before, like SkipInit. They have now, after this came the NFNet, and just 10 days ago there was this paper of using multiple augmentations that has achieved state of the art. But yeah, we will get all through that. But this line of research is really key, and I really like this paper just because of that, the results that we can see from the paper. Cool. So that's this. So in this introduction, basically what happens is what the authors say is that batch norm has become a core computational primitive in deep learning. So basically in every architecture that you see today, or every architecture, every computer vision architecture that you would have used, you would have seen that batch norm is there. And then it actually is, like we look at, say, efficient nets, we look at rest nets, we look at even the vision transformers. The batch norm is a key component, and it there's a reason why the batch norm is a key component, because it smoothens the loss landscape, it allows larger learning rates, and it allows good signal propagation at initialization. So something, when we say good signal propagation, what we want to do and what we want to make sure is that in our network, the mean is 0 and the standard deviation is 1 of the activations. So that's something that we want to make sure in our network. So that's what they say. And because of these benefits, I mean, batch norm, when it first came, it was like, oh, it's like magic. It can really help with a lot of things. But over time, people have realized that batch norm also has some disadvantages. Basically, when the per batch size is too small or too large, so if you're trying to do segmentation, if you're trying to do object detection, which isn't the case more so in the year 2021, but I feel like if the image size is so big, like if you're training with a really, really big image size, then you can only fit a certain amount of images. And when you fit a certain amount of images, you can only, when it's like the batch size is 1 or 2, then those batch statistics that you calculate, like what batch norm does, it calculates the mean and standard deviation, and it normalizes the batch. That becomes very unstable. And as a result of that, so when the batch size is so small, the result of that is that the performance isn't as good. So there's like these points which have been highlighted. This is like when the batch size is too small or too large, you want to replace batch norm and you want to find alternatives. It adds a memory overhead. It's a common source of implementation errors. By implementation errors, basically, I believe, from looking at their open review discussion, I believe they meant like when you're trying to use the pre-trained weights, or when you're trying to fine tune, I think batch norm is at the key of implementation errors. This is where they say it is often difficult to replicate batch normalized on different models trained on different hardware. Cool. So that's the gist of it. So batch norm is good and batch norm is bad. Sometimes batch norm is considered as a necessary evil. So this whole section was on batch norm. So another line of research that has sought to eliminate layers which normalize. So this is the line of research that this NF-ResNet paper is based on as well. And in this line of research, basically, what the authors have tried is we want to remove batch norm, and they're not the first ones to try and do that. Like there's these past papers that have tried to do it, but they're the first ones to actually achieve very competitive results to their batch norm counterparts. So there's two kinds of networks: without batch norm and with batch norm. So generally the with batch norm were really good. Like they would say achieve 85%. And I'm making this up, but around, let's say around that mark, they have ImageNet top 1 accuracy. Without batch norm, until before this, you would have like a really smaller ones, but this one is really competitive. Like it can go 84.5, or you can even go to a point of 84.8. And I'm making these numbers up, but that's the main idea. Like this paper is the one that has made networks without batch norm come really close to the networks with batch norm. So the key contributions from this paper, and we're going to be looking at all of them in a lot of detail. The first one is signal propagation plots. Next, they say this is about weight standardization. So they also introduced something called scaled weight standardization. And I'll go into the story of like how scaled weight standardization came into play and like what it is exactly. First, we'll look at what weight standardization is, and then we'll look at what scaled weight standardization is. And then finally, this is what I was saying. It's the first time that we attain a performance which is comparable or better than batch normalized ResNets. And lastly, they apply it to the RegNet architecture. And based on this, they're able to get state-of-the-art results, which are very close to the existing efficient nets. So that's that. Okay, so we're going to start with looking at SPPs. Then we're going to start and look into weight standardization. And then we're going to look into this point here. Any questions so far? And if there are any questions, let's go to 1db.me/nfresnet. So I'll bring it up. Okay, it's this one. Are there any questions so far? So the question is, why does batch norm not work for small batch sizes? As I said, with small batch sizes, so you got to understand what batch norm does. So when you have a batch, let's say you have 8 by 3 by 2 to 4 by 2 to 4, which just means like you have 8 images of 3 by 2 to 4 by 2 to 4. Then what batch norm does is it calculates the mean and it calculates the standard deviation of this batch. So of this, basically these 8 images. And then it will subtract by the mean. So divides by the mean and divides by standard deviation, and that's how it normalizes. But basically then the main idea is if this batch number is too small, then this mean and standard deviation, they become unstable, and it becomes really hard to train a network with a really small batch size. That's the main idea. Cool. With that being said, let's start with signal propagation plots. Okay. So something that the authors mentioned at this point is there's been a lot of studies for batch norm. There's been lots of studies on how batch norm affects the signals. There's been lots of studies on how batch norm is you know, how basically the network, how the signal goes through the network. And what they try and do is, so let me show you. So let's say this is my deep network. So I'm just calling it like, this is my ResNet 34. Actually, I should have a, okay, this is my ResNet 34, right? That's my deep architecture. What the authors do is they first initialize it. They first initialize this whole network architecture. And then instead of passing in, you could pass in real input images, but what they do is they say, we're going to pass something of a Gaussian distribution. It's not that important to know why, but you could also pass in real, images. And what they try and do is when this thing will go, so let's say the image, let's say just this is just 8 by 3 by 2 to 4 by 2 to 4. So basically you have 8 images of 2 to 4 by 2 to 4 and 3 channels. What this does is when this goes through the whole network, what they're doing is they're calculating some statistics. So these things are called activations as they go through the network. And what they're doing is they're calculating some statistics and they're plotting them. And that's SPPs basically. So in signal propagation plots, and the reason why signal propagation plots are important is because what the authors try and do is they first use signal propagation plots to look at how batch norm behaves. So they understand exactly how batch norm behaves. And then based on that, they try and replicate that with non-normalized networks, basically non-batch norm networks, and they try and mimic the pattern. So if you think of this, like if you know how something works exactly, and you try and mimic it, like you try and mimic the pattern, then you're bound to have something that also works. So what they do here is they plot these signal propagation plots, and they plot basically three things. So when I told you, like when I showed you, as the thing goes deeper and deeper into the network, what they do is they plot three things, and I'll show you how you can do it in your own experiments in PyTorch as well very quickly. So they plot these three things: average channel squared mean, average channel variance, and average channel variance at the end of the residual branch. So basically, you know how to calculate mean. It's just in Torch, you can just go, torch.mean, and then you provide the axis. But basically, they're just calculating the mean of the activations, and they're calculating the variance. And then this is the one at the end of each residual branch. And something that they notice is when they plot it. So they plot it for two orders. The first in the blue at the top is the batch norm ReLU ordering. So basically, you have your convolution batch norm ReLU, and in the second one they have a ReLU and batch norm. And one thing that they notice, they plotted for a ResNet V2600. It's just a network architecture. And one thing that they notice is when they plot it, this pattern emerges. So if I'm looking at this one, so the batch norm ReLU, basically I'm looking at the batch norm ReLU. That's this one, and the pattern emerges that for average square channel mean, the mean first goes up and then it crashes. Then it goes up and then it crashes. And it doesn't, when I say crash it, I mean it goes back to 0. So it goes up and then it goes down. And it's the same thing that can be observed for average channel variance. It's like it goes up and then goes down. It goes up and goes down, goes up and goes down. And what the authors were trying to do is they were trying to understand exactly how batch norm behaves in a network. And while there has been so much theory and there has been like so much talk of like how batch norm behaves, there hasn't really been a practical way of sort of visualizing it. And the reason what happens is, so you can you imagine why the squared channel mean would go up? The reason for that is very simple. In a batch norm ReLU ordering, so what is ReLU? Well, ReLU is something like a max 0 or H if my activation is H. So what ReLU does is, if anything is negative, it will set it to 0. So as we go through the network, so if this is my, these are my 4 blocks, let's just say, and as we go down into the network, what ReLU is going to do is it's going to keep making things positive and more positive. So that's what ReLU will do. It will remove all the negatives. And when you remove all the negatives, the mean goes up. So if you have your -1, -2, 0, 1, 2. When you have something like, let's say I have 5 activations, which are this, and the mean in this case is 0. But when I pass it through a ReLU, it will set these to 0, and suddenly the mean becomes 1.5. So you can see how the mean will keep going up and up as we go down into the network because of this batch norm ReLU. The same thing happens with variance. So with variance, they say that the network is variance preserving, as in what they notice is that there's a constant addition of some part of variance to the activations. And what they say is, like, this is the pattern that we want to mimic. So they basically look at these two things, these two charts, and they say we want to mimic this pattern. And they also look at average channel variance. And this one is set to 0.68. That's because this one is just set to 0.68, and they have a massive explanation of what exactly it is. I won't go into the very detail of what exactly that is, but the main part, as long as we as a group understand that we want to mimic these patterns, then we could. So that's the first thing. So that's exactly what signal propagation plot is. And let me now show you how you can actually plot signal propagation plots in TIM. So in the block, so you can see how, so this is just a way of showing you how. So as part of writing this block, something I did was I try and experiment things for my own sake, and I try and understand exactly, like, okay, this is what the paper says, and is this what exactly is happening? In TIM, TIM is a library called PyTorch Image Models, which is maintained by Ross Fitman. I contributed these extract SPP stats. So what this does is basically as your So as the network, so this just plots the way, this just plots the SPPs. It will first extract the SPP stats, which is just, as I said, we want to extract these, as we go down, we want to extract these stats at like, of the activations at various positions. It will extract the SPP stats and it plots the average square channel mean, the channel variance, and then the residual, which is exactly what we want to see. And you can see how that's exactly the same pattern as what is in the paper. So it was really good for me to see, like, I can replicate these results in code, and you can also try and do this if you follow that blog. But that's the main thing. Cool. So that's the first side of things. And the same authors have written past papers, which is called the skip init. And I'm just going to provide some background on exactly what that skip init paper does. So what the authors saw is like, if you have a network, so you have your convolution here, then you have your convolution here, and you have your inputs coming in from here, and you have your skip connection, right? What the authors saw is when you go, of course, this has bash norm as well in it. So when I say conv, it's just a conv bash norm ReLU. That's just standard. When the inputs go like this is just one block. So this is just a copy of this. So that is just this much. And then you have the whole network, right? So what this does is after this shift, you still have the whole network at the bottom. What they realize is that what bash norm does is that when the signal, so a signal has two options, right? The signal can go down this path. So the signal can go down this residual path, or it can go down this skip init path. Well, it goes down both the paths. But what the authors saw in the skip init paper is that what bash norm actually does, like, it's just about understanding first exactly what bash norm does, and then repeating that and mimicking that pattern to design non-bash norm networks. What they saw is like it changes the signal, it attenuates the signal. What it's trying to do is if you have an input here, it will reduce the signal by some ratio, which is under root L, if L is the number of layers. So what that means is, if I'm a ResNet 34, what bash norm will do, it will reduce the signal value on the residual branch by under root 34 factor. So that's just one of the things that you should remember, or that you should know, is that when a signal is going down the residual path, bash norm will reduce the value of it and will divide it by some number. That's the main thing. And that's the skip init paper. Like it was a really good paper to read, and that's the main summary of it. So by now we've looked at exactly how a signal behaves in a bash normalized ResNet. What the authors now do, this is the main bit. What the authors now do, they say, my signal is going to look like this. XL plus 1 equals XL plus alpha FL XL by beta L. What does that mean? Like, this is just all some math that I do not understand. And the only way that I understand things is by sort of drawing them. So what they say is, let the input is XL. So this is your residual branch, and this is the skip connection that gets added, right? So they call this residual branch as FL. And what they say basically is that when this, so we know from the skip init paper, we know that what bash norm will do is it will reduce the signal by some factor. So if I've called my signal XL, we want to reduce the signal by some factor, and they call that factor beta L. So that's XL by beta L. So they say, okay, this side is going to reduce the factor by beta L. That's the first thing. The second thing that they say is we want our variance to increase. So you have this. So your XL comes all the way here. The output of this is FL XL by beta L. Then they multiply it by a number called alpha. So you get alpha FL XL by beta L. So you get this part. And finally, you add the skip connection from here, which is plus XL. So that's how they design the normalizer free network. Like this is the main part. They designed the normalizer free network like this. And like this is just the theory of it, like how they ended up designing and what's the thought. So they basically they've looked at exactly everything that Bashnorm does, and they've tried to replicate it in a non-Bashnorm network. So if I go into the theory of it, I'm really sorry, this paper is a lot math heavy, but to understand it completely, like we need to understand the math. And what they say is, I'm going to set beta L equals to under root where basically the square root of variance of the input. What that means, so my input is XL and beta L is set to this, right? It took me, I'm not from a mathematics background myself, and it took me like 2 weeks to understand exactly what's going on. Or like I pretty much spent 2 weeks just trying to understand, oh, why did they design the network like this? What exactly is going on? What is alpha L? What is beta L? Without going too much into detail, but I still want to be able to explain like these sort of things. In the blog, you'll see everything that explains all of this, all the math that's written here, in like all the questions as well, like why is beta L chosen to be square root variance XL, which is the input. The answer is like when you divide an input by the square root of its variance. So if this is my input and I divide it by the square root of its variance, that makes sure that my variance is of that thing is equal to 1. So I have unit variance. So something I've already said, we want to make sure that the activations have mean 0 and standard deviation 1. So this is a step in this direction. Okay, that's the idea. And the next thing that so this is the main bit. And the next thing, that the reason why they have this alpha over here, so this will add some variance to my input signal. And the reason why they have this alpha is because when I looked at my last figure, I saw the average channel variance go up by a certain number until it crashes. So they want to be able to mimic that. Like they want to be able to increase that variance by a constant factor, that constant factor is called alpha. So if we go into the blog and let's have a look at what exactly is alpha. So I've already spent like a lot of time on this paper just trying to understand exactly and everything that's going on. But let me just copy paste this bit. Okay, so we know that our network is designed like this: XL plus 1 equals XL by this. That's basically to say my input is XL, my residual branch is FL, so that's my residual branch. This is my skipping it, and that's that. And there's an alpha, which is the scalar that gets multiplied here. And there's a beta, so I just divide by beta L. So the input goes here, it gets divided by this number beta L, and then goes all the way down. So we know that beta L is chosen to be, we've already looked at this. Like why is beta L equals to this? It's because we want it to have unit variance. So therefore, this thing, XL by beta L, has unit variance, right? Something that the authors say is that this residual branch is variance preserving. All that means is if you have a function f and you have an input XL, whatever the variance of this thing is, f of XL will have the same variance. That's exactly what it means by saying that this is variance preserving. So this is my equation, right? If I take the variance, like if I'm calculating the variance on both sides, then this is what I get: variance XL plus 1 equals variance XL plus this. We know that this thing, FL XL by beta L, has unit variance, in that case, the variance then just becomes this. So this alpha, the variance of it is alpha squared. So this is how this looks like. And as I say, it took me 2 weeks to get to this point and understand exactly what's going on and like, why is this equation equating to this? It's just mentioned in the paper. So that's the main idea. So now, so see how they mention it here? Variance XL equals variance XL minus 1 plus alpha squared. Now you exactly know why, and you exactly know what's going on. So this is the main idea. Like this is exactly what they did. I think at this point we've kind of understood exactly in everything that's going on in a normalizer free network. We've like the main idea is this: if you want to remove bash norm from the network, what you do is you first understand exactly what bash norm does in that network, which they did through these signal propagation plots, which is these ones here. So they looked at and they understood that they understood exactly how that particular element that we want to remove, which is bash norm, behaves in that network. And then they went in and they plotted these three things, which gives us that signal propagation plot. And then they went in and they said, okay, I'm going to design my new network based on this equation, which we've already looked at. This is the equation. And then they went in and they said, okay, I'm going to design my new network based on this equation. And the reason why they designed this new network based on this equation, like this is how the new normalizer free block becomes, it's because they want to mimic everything. Like they want the variance to increase by a constant factor, which gives me this. So this alpha squared is the constant factor by which the variance increases. So this way I can replicate this chart over here, and by the other one I can replicate this chart. So this is just the way of being able to replicate those charts. So moving on in the paper, this is just them explaining like ReLU activations induce mean shifts. This is just them explaining, which I've already explained to you, is like why is the mean going up and it keeps on going? It's because of this. Like when you remove the negative numbers, then the mean is bound to go up. And this is just them explaining that. Okay. So that's the main thing. So then what they did, now we're coming to the scaled weight standardization. But before we go in, here's what they did. So they plotted that. They plotted this whole thing. Like this equation that we've just seen, they plotted that and they looked at the signal propagation plots. And the one thing that they noticed is that it doesn't look like what we want it to be. So the average square channel mean is still going up. The average square channel variance is going up, which is good. Like this is kind of what we're trying to mimic. But when I said we want our mean to be 0 and variance to be 1, well, that's still not happening. Like, how do we make sure that we have good signal propagation? The next thing that they introduced after doing all of this and after understanding, the next thing that the authors introduced is something called weight standardization. So what is weight standardization? So this is the paper for weight standardization. This is exactly what weight standardization is in figure 2. Basically, in figure 2, what they're trying to show is like in weight standardization, what bash norm does, bash norm is trying to normalize the activations, right? And what weight standardization does, it's trying to normalize the convolution weights instead. So what that means, I'm just going to show you quickly. I have my conv here. This is my skip connection. So what bash norm will do is if this is my input and I get I dash here and I get pretty much my output here, and the thing is output plus input, because that's the skip connection. What bash norm will do, it will try and normalize this. So it's normalizing the activations. It's basically normalizing these inputs, not the input exactly, but things that are coming out, like things that are coming out. Like this is the activation, this is the activation, and then finally the output, like the outputs of things, basically. That's what it's trying to normalize. What weight standardization does, weight standardization said, instead of normalizing these things, which is the activations, let's normalize the convs instead. Let's normalize these. And by normalizing, I mean, it's just this, right? You take the weights, you subtract by the mean of it, and you divide by the standard deviation. And that's it. So this is what this does. This scaled weight standardization, it pretty much just introduces these two new things as opposed to weight standardization, which are just scalars. This is called a gamma. The gamma will have a different value based on the activation. There's a lot of theory that they go into, which is explained here. I don't think it's necessary for us to understand, like, I believe as long as we understand the overall, meaning of what exactly is going on in NF-ResNet paper, there's things we can skip for the first time. Like if we dump and if we like, that's just one way of reading a paper. And it's something that I do is like, I read a paper in multiple passes. So the first pass for me is to look into and like understand the basic, like what's the introduction, what's the abstract. Then I do my first pass, which in first pass I will look at things like, okay, like this, let's go deeper into the figures. Then my second pass would be, okay, let's go deeper into what is weight standardization. Like I come from a background as well where I didn't know what weight standardization is. I didn't know what how this thing has unit variance and all that stuff. So like the second pass will help me understand the math. Then the third pass will help me replicate this in code. And we have that. So if you want to try the NF-ResNet paper, you can do so in PyTorch and JAX. So just in that, I've shared it in the chat. But Tim library is one of the best to get started. And I can just go tim.create model NF-ResNet 50, and then I can experiment with my NF-ResNet model. And I've also plotted like these. I've also plotted all of this stuff using NF-ResNet, which you'll find in this blog. But one thing I do want to also want to look into, given we have less time left. Something that I also want to look into is weight standardization. And this is what is weight standardization. So, when we were looking into weight standardization, I said the weight standardization basically does this, like it looks at these convs instead of like it normalizes the weights of the convolutions. Something I was looking into is this weight standardization, and this is how it is implemented. You just basically subtract the mean. You calculate the mean, you subtract the mean, you calculate the standard deviation, and you divide by standard deviation, and that becomes your weight standardization. Like that's really as easy. I mean, things look so complex when you're trying to read them in mathematics, but to me, like things look really easy when I look at them in code. And this is what you should do as well on the side. And when I was experimenting, it's like this is I was experimenting with group norm, and I was looking at weight standardization as group norm and weight standardization. And when I was looking at this, weight standardization and group norm together actually gave me really good results as compared to batch norm. So that's so these are things that I just want to take like 2 minutes and say, I'll post this in the chat as well in case anybody wants to try. And this is part of the group norm blog. Yeah. So that's exactly it. Like that's all there is to the NF-ResNet paper. We want to remove batch norm, and this paper is able to do so. And by then implementing with, by then introducing weight standardization, scale weight standardization, you can see how, you can see how these results are really competitive. Like ResNet 288 gets like an 80% accuracy on ImageNet. And finally, what they did was, this is the main bit. Finally, what they did by having everything, like having my equation as this, XL plus 1 equals XL plus alpha F of XL by beta L. So this becomes, so a ResNet is basically this, right? XL plus 1 equals FXL plus FLXL. Like that's just a mathematical way of writing a ResNet. This is the ResNet. This is the NF ResNet. So why is this the ResNet? It's just, this is my residual branch. This is my input. The input passes through this residual branch. So what they did then, they applied this technique to this RegNet paper, which is, I looked at it like a month ago. It was just basically like the design, you design spaces, like it's like a reinforcement learning sort of way of designing the network architecture. And they applied this to this because it had really good results at the time. And you can see how NF RegNets with cut mix and mix up augmentation have really competitive results with efficient nets. So that's the gist of it. That's NF ResNet. From here, from this point on, if you really want to like follow me along in this journey of reading deep learning papers, I've given you everything that you need to understand the NF ResNet paper. If I were you, I would pick this up. I would read the blog as a first introduction. Then I would read the paper. Then I would go to Tim to try and experiment. And then finally, then I have a really good understanding of exactly what NF ResNets are. And if you want to experiment in the end, then that's just cherry on the top. But that's NF ResNet. So let's go into questions. Okay. So the last 10-15 minutes is usually questions, and something I do encourage is like, I really want to say, if you guys want to turn your mics on or if you want to talk to me, then I think this would be brilliant. Why does batch number, this has been discussed. What is RegNet? Is it just ResNet with slightly different architecture? No, it is not. So the RegNet architecture, I think it was by Facebook. Yeah, it is by Facebook. So the RegNet is just, it's called designing. This is not it. RegNet design. That's the paper. So we can also look into the RegNet paper. It's really interesting as well. But basically, like, if you have a theory, if you know exactly how efficient nets are designed, efficient nets are designed by using reinforcement learning. So just sort of going into digressing a little bit to tell you what the RegNet paper is. But this is how the efficient nets are designed. You have a controller, you have a trainer, and you have some objectives. And then based on reinforcement learning, like this is similar to the MNASNet approach. Based on reinforcement learning, you try and find an architecture that really does and work well for you. And RegNet sort of is a different way of doing the same thing, in that they say we're going to design network design spaces. So having a look, I mean, go through that paper. But it's very different from a ResNet. Large batch size should not be a problem for BashNOM. No, it isn't. But if it's like, you've seen networks that have been trained with, like, even I've experimented with the networks that have been trained with really large. But the one thing that I've seen in the past papers, and I've not experimented with it, and it's just because I lack the hardware. I've seen papers mention like a really large batch size is a problem. So a large batch size is not a problem, but a really large batch size. And what exactly does that mean? Is that like because like we look at the recent papers, if you have a look at like efficient at V2, or if you have a look at the vision transformers, they all train on TPUs and they all have batch sizes like 5 and 2, or they have 256, or sometimes even 1024. And for those batch sizes, you do get state-of-the-art results. So what exactly, at which point does BashNOM start to give a problem, and what exactly with sort of batch size? That's for me yet to explore. Aditya, for this to happen, graph study showed activations should strictly increase layer by layer because we are already applying BashNOM, isn't it? I don't understand, but I guess, sorry, if you want to post your question again, that would be helpful. But if my understanding is like, let's go back to the graphs. So these graphs are layer by layer. Like a ResNet V2 600 has 600 of these blocks like on the side. So after everything they calculate, So it's like it is, if that's what you meant, it is like that. Why does the average, mean, and standard fall down at the end of each block? Oh, that's a really, really good question. Thanks for asking, Pranav. Okay, so this is a really interesting question. So if I go in the ResNet, right? So you can see in here in the ResNet, like this is my first block, right? And this is 64 channels, and this is my second block, and this is 128 channels. The minute I go from the first block to the second block, like I'm going from 64 channels to 128, we also downsample the image in ResNet, and this is not even like NF ResNet, this is just ResNet. We downsample the image. So I'm just going to write downsample here. And because we downsample the image, so look at this. If my image size here is 3 by 2 to 4 by 2 to 4, if I downsample it and it becomes 3 by 112 by 112, sorry, if it becomes, say, if this is 64, because it's 64 channels. So let's just say it's 64 by that, and then this becomes 128. Then what they do, like this skip connection, because at this point, the input is of this size and the output is of this size, right? So the sizes are different. So you can't really add them. So what the skip connection, in that case, it's not just a skip connection, there's a convolution that downsamples the input as well. So this thing has a convolution in it. It's like a 1 by 1, or like, it's pretty much just downsample your input. Sorry, it's not a 1 by 1. But there is a convolution to downsample the input. And when you have a convolution to downsample the input, then any growth that happens is reset. So at these points, like these points, this is where that block is being changed, and you have a convolution in the skip path, basically, and that's where the growth is reset. Okay, Prasanna, you say the mean reduces by a factor. No, not the mean. Oh yeah, as it passes through the batch norm layer, but the graphs show that the average square channel mean increases as we move down the blocks and then drop to 0. Okay, I guess what you're trying to say is, okay, I guess what you're trying to say is, what I said was you have, like this is how this looks like, right? And I said you have your input here, and this is my residual branch, and this is my skip branch, basically, or shortcut branch. So what I said was, we go, if it's like we reduce, like what we've seen is batch norm reduces this by a certain number, so it reduces this. But that's not to say that the mean reduces, because you still have your input signal coming from here, right? And the output of it becomes I plus I by under root L. So that way, like the mean can still go up. But this is to say that what it does, what batch norm does, is that it biases the, if you think of it, like if most of my signal passes through here, then in my forward and backward pass, there's not going to be any problem. There's not going to be any problem in my forward and backward propagation, and my gradient will never explode, as long as like they're going through the shortcut path. So it's much easier for the inputs to go through the shortcut path than for them to go through the residual branch. So that's what I meant. I didn't mean to say, like, you can see how still the mean will go up because you still have the skip init input. So I hope that answers that. Oh, one second. Okay. All right. Is alpha a constant? If so, its variance, shouldn't it be 0? If so, could you please explain why variance alpha is alpha squared? Alpha is a constant. So that's why the variance of constants is like the square of it. I mean, this is the bit where, like, this is the statistical bit where because alpha is being, so when I say alpha is a constant, the variance of the alpha itself would be 0, like that's my understanding as well. But when you're multiplying, because it's the, so if you're alpha L, FL, XL by beta L, right? And this thing has a unit variance. So the variance of this whole thing becomes alpha L squared. That's the idea. Like, it's not to say that the variance of alpha L is equal to this. No, the variance of this whole thing with this as the unit variance, this becomes alpha L squared. Like, that's my understanding. So I hope that helps. And this is exactly what I've sort of tried to say in the paper. So since it's a scalar parameter, sorry, oh, there it is. So basically, when you take the variance at this point, this is what gets replaced by alpha square. Okay, why average squared mean is decreasing with depth? Oh, it's completely the opposite. I think average squared mean is increasing. So you can see how, yeah, the mean is going up. Is it possible to use NF-ResNets for image semantic segmentation tasks like general ResNets and ResNext? Yes, totally. I think the best way, if you're a PyTorch user, I think the best way to start would be to go with, you pretty much start with Tim, which is one of my go-to libraries, and you just create your model, and then with that model, you can try and do anything that you want to try. I have a doubt, Conjure Day. I have a doubt. I played around with Tim NF-ResNet. I compared pre-trained NF-ResNet 50 with Torch Vision pre-trained ResNet 50. Can you tell me, are they both trained on same ImageNet or not, as it is much more accurate on same images? So when you say this, sorry, could you please reply to this thread, or just say when you say it's more accurate on same images, do you mean to say NF-ResNet is more accurate than ResNet 50? Or you could just say yes in the chat if you're around. So you've said NF-ResNet is more accurate. Basically, it's because it's not just like, just in the paper reading group, like 2 weeks ago when we were looking at the ResNet RS paper, we looked at, like, it's not just the network that's important. There's like so many other things that are important too, like the data augmentation, like the training recipe. So if you train the network with augmentations, like there's definitely a possibility where NF-ResNet 50 will be more accurate than ResNet 50. But this is definitely a PyTorch image question. So if you want to ping Ross, you go to here and you can just go to issues or discussions, and you can just ping Ross, and you can ask a quick question on what exactly was NF-ResNet trained on, like what are the exact hyperparams. Any idea why group norm and weight standardization gives better results? Absolutely. So this is, I would refer you to a previous blog on group norm, but the idea is weight standardization will also standardize the convolution weights, which makes sure, like when we're trying to, it makes it, so the theory of it is, like from what I've read, the theory of it is if your weights have a mean 0 and a standard deviation 1, and like if the, so let's see, like this is my one of the loss landscapes, and this is my second one. A smoother loss landscape is much easier to optimize than something like this. On the other hand, like this one is much harder to optimize, and but doing something like this, we make sure that the loss landscape is smoother. And this is one of the reasons like why Batchnorm is so successful, and this is one of the advantages that you'll read pretty much everywhere, is like Batchnorm takes Batchnorm makes things like Batchnorm smoothens the loss landscape. So then when you have weight standardization, what you're trying to do is you actually want to optimize the weights of a convolution, right? When they already have mean 0, standard deviation 1, it's much smoother and much easier to optimize. So that way the scaled, and you can follow this notebook to experiment for yourself, but that's my understanding on why this works. Okay, beta L is calculated, or is it calculated from the first? Oh, beta L is a constant under root variance. Or is it calculated as approximation? No, pretty much you have your inputs. From my understanding, like I've read this from what I've seen in the implementation side of things, is like you just calculate beta L once, and then that's your under root variance, and then you go on with it. So if we assume Bashnum comparable results in this paper are true, does that mean models will make it both faster? And oh yes, that's a really good point. Like that's the whole, so I want to point you to NFNet paper. In NFNet and the recent multiple these ones. So these are two papers that you should also read after this. In high performance scale image regularization, they say, oh, here we go. Our smaller models match the test accuracy of an efficient B7 and while being 8.7x faster to train. So these are the same authors who first worked on NFResNet, and they ended up designing the NFNet paper. And our largest model attains new state-of-the-art accuracy of 86.5. So NFNets, normalizer free networks, work. NFNets are able to achieve state-of-the-art, and they are definitely faster because of it takes away all the memory overhead and takes away all the computation that Bashnum does. Something I also want to point you guys to is just this very recent paper that came about, well, 15 days ago on 27th May. It's drawing multiple augmentation. In this paper as well, they use an NFNet, and they use a strategy of drawing multiple augmentation samples. But this also achieves a new ImageNet state-of-the-art of 86.8. So while the same authors got 86.5, this one gets 86.8. So without any extra data. So I should definitely like recommend you guys to for this to be the next paper that you guys read. How they make sure there are no vanishing or exploding gradients. Thanks, Animesh. That's a good question. Like this whole idea of like having a unit variance, like the divide by a beta L, which is the under root variance, making sure that XL by beta L has unit variance. I think that's the, like, as long as your forward pass has a mean 0 and standard deviation 1, then that's good enough reason to think that the gradients will not explode. And the authors have made every effort to make sure that the mean is 0 and standard deviation is 1. But that's what they make sure. And something that's in the theory of ResNet that I've read in one of these papers is that they say, as long as ResNet has a good forward pass, the gradients will not explode on the way back, which means the backward pass. I don't understand the next question. What is team or theme? I can't. Oh, I've been saying team, so I'm not saying team.
It was already taken by someone from the chat, so I guess it was referring to the TIM library.
Oh, TIM. Yes, TIM. Okay, so it's called PyTorch image models. I'm really sorry for the confusion. It's called PyTorch image models, but the abbreviation of it is called TIM. And that's it for today. Thanks everybody.
Here's just one more question. Whether you could post the papers you just mentioned as a recommendation, because I think it's really interesting for people to read.
Oh yeah, sure. Let me post them right on the paper reading group here. So that's one.
Thank you.
Cool. Thanks everybody. I will do. See you guys next week, where we're looking at next week. Yeah, next week we're looking at Convit. Sorry, that's the 15th. So see you guys, and see you next time.